It is often easier to translate real-world situations to a system of two equations that use two variables or unknowns than it is to represent the situation with one equation using one variable. Let's see how the following problem can be represented by two equations using two unknowns. The perimeter of a basketball court is 288 feet. The length is 44 feet longer than the width. Determine the dimensions of the court. Here we have a rectangle representing the court with W for the width and L for the length. Given the perimeter or distance around is 288 feet, we can create the following equation. Simplifying by combining like terms gives twice the length plus twice the width equal to the perimeter given. Looking at the other piece of information in this problem, we can create an equation representing it using the two variables. Length is 44 feet more than the width is the translation or representation of that second equation. These two equations form a sister system of equations that must both be true. A system of equations may have one solution, no solution, or an infinite number of solutions. A solution to a system has to make all of the equations true when substituted. And here we have our ordered pair, which typically we list the variables in alphabetical order unless stated otherwise. So looking for a solution, length and width, that satisfy both of these equations, let's run a trial. We're going to replace our length with 94 and our width with 50 and see if it holds true in both of these two equations. Length is 94, width is 50. In the first equation, we'll multiply both of those values by 2. Adding on the left side gives us a true statement. To see if a length of 94 and a width of 50 is true for this system, it also has to satisfy the second equation. So replacing L with the value 94 and W for width with 50, simplifying on the right, we see that this is also true. If it checks in both equations, then this ordered pair is a solution to the system. Let's look at another example for a possible solution to this system of equations. Again, we have the ordered pair, length and width, and let's replace length with 90 and width with 46. So let's plug them in and see what happens. In place of L, we put 90, and W is replaced with 46 in this first equation. Taking care of multiplication and then addition, we see right now a contradiction. It has to be true in both equations, so we could stop and know that this is not a solution, but just to show, replacing in the second equation, length with 90, width with 46, it does hold true here. Regardless that it's true for one, it is not a solution unless it's true in both of the equations. A system of equations is a set of two or more equations that are to be solved simultaneously. A solution of a system will make all of the equations true. And to solve a system of two equations is to find all ordered pairs, if any exist, for which both equations are true. We've seen an example here where one is true and where the other ordered pair is not true.